Hello, everyone. Let's get started on going through some of these exam practice problems. So we will be reviewing the complete treatment F-level exam, and we will be going through the calculation-based questions. So let us pull out the exam and let's dive right into solving some of these problems and have them solved by hand. There was a request to have someone go through the step by step, kind of walk through some of the logic. So with the very first calculation-based question, we have is number 2 here. It asks, you want to dilute a standard 0.1 sulfuric acid to 1 liter of 0.01, and it asks how much of the 0.1 acid do you need to use, right? So the very first thing you want to do to get a dilution from one normality to the other, you would first need to know what equation you need to use. So from our equation sheet, now a little bit of a breakdown on the equation sheets. You have your conversion factors, which you can convert from one unit to the other, continued conversion factors, and you also have your flow and velocity or flow equation right here. You have your area equations here, volumes. You have your horsepower equations. You also have your total dynamic head equation, some alkalinity information, some common compounds in water and their chemical formulas. We also have some miscellaneous formulas such as the leakage formula, the pumping rate, etc. on the second page, right? And then followed also by the elements and their atomic masses. So just a little bit on the formulation sheet, right? Here you have your chemical dose required, depending on your source of demand. So the equation that we are looking at for this question is the dilution equation, right? You have concentration 1 multiplied by volume 1 is equal to concentration 2 multiplied by volume 2. So this is the equation that we need since it is asking in the question that we want to dilute a standard from one normality to the other, right? So let's take a look first at what we have, right? So we write down our equation. Concentration 1, volume 1 is equal to concentration 2, volume 2. That's multiplied by, right? So concentration 1 from the problem statement, let's write down everything we have. Concentration 1, 0.1 normality, right? We also have concentration 2, which it tells us that we want to dilute it to have a normality of 0.01 molar, normality, right? We also have volume 2, that's equal to 1 liter, but again, in our answers, we have our answers in milliliters. So 1 liter converted to milliliters, right? 1 liter is equivalent to 1,000 milliliters, right? We want to kind of have those units so that we have our ending units, our volume 2 in milliliters as well. So now we want to put everything together, right? Plug everything into the equation. 0.1 normal multiplied by volume 1 is equal to 0.01 normal multiplied by volume 2, which is 1,000 milliliters, right? So now what we want to do here, do some basic algebra. What we do to one side, we want to do to the other. So if we divide this side by 0.1 molar, we do the same thing to the other. Divide by 0.1 normal. These concentrations, C1 cancels itself out over here, and then we're left with the equation. Volume 1 is equal to 0.01 normal multiplied by 1,000 milliliters divided by 0.1 normality. So we can take this step by step to get our overall equation, our overall answer. So if we want to multiply everything on the top first, so 0.01 multiplied by 1,000, right? that gives us 10. All right, so that's going to be 10 divided by 0.1, right, to give us our volume 1, right? Divide that by 0.1 to give us 100 milliliters of that volume 1. Now, what does that mean? What does 100 milliliters mean? 100 milliliters, that is the amount of the higher concentration solution that you need to take, that's a sample, and dilute that to 1000 milliliters to get that 0.01 normality solution, right? That's what that means. So we take a look at number 2. Again, 1000 milliliters. The answer is B. That's, sorry, 100 milliliters. So that 100 milliliters is what you need to dilute up to 1000 milliliters total to have that concentration of a 0.01 normality, right? And that's the amount you need to use, 100 milliliters. Let's go ahead and take a look at the second one. So next question, it's calculation based, is number 4 on the practice exam. All right. It says calculate the percent sulfur in iron 3 sulfate. Right. We have our equation here. Right. And we want to calculate that percentage of specifically sulfur. So the first step we want to take, we want to get the atomic masses of each one of these elements, right? Of iron, sulfur, and oxygen. So let's look at our periodic table, or AKA our formula sheet, which has all of these on hand. Let's first write our formula. Iron, right? From our formula sheet, we have iron as 55.85. We have sulfur at 32.06 grams. And then we also have oxygen, at 16.00 grams. So let's write all these down. Let's write those molecular weights. Iron, 55.85 molecular weight grams. Sulfur is at 32.06 grams, right? And then we have oxygen, which is at 16.00 grams, right? So the next thing we want to do, we want, again, to find that percentage of sulfur in this molecule, right? The molecule itself, if we read it out, has 2 iron, it has 3 sulfurs, and it has 4 multiplied by 3, it has 12 oxygens, right? So we want to find that weight, the total molecular weight for this molecule, right? So let's go through and do that. So for iron, the total weight of iron in the molecule, 55.85 grams, multiplied by 2, we get 111.7, right? Then we look at sulfur, molecular weight 32.06 grams, and we have 3 of those, right? From our overall molecule, we have 3 sulfurs multiplied by 3, 96.18 grams, right? Now for oxygen, molecular weight 16.00 is the atomic mass, sorry. We multiply that by 12, right? Because we have 12 oxygens total, 3 multiplied by 4, 12 oxygens, right? So 16 multiplied by 12 to give us 192 grams, right? So the total weight of the molecule, will be the addition of all these masses, right? Total weight equal to 111.7 grams plus 96.18 grams plus 192 grams, right? Let's go through, add those up. 111.7 plus 96.18 plus 192, right? To give us a total weight of 399.88 grams. So that is the total molecular weight of this molecule. Now, to find the percent sulfur in the molecule, we have how much sulfur we have, right? In this molecule, 96.18. We calculated that right when we were tallying up all the all the weights of the individual elements in the molecule, right? So the percentage, you have 96.18, right? And that's grams of sulfur divided by the total weight, 399.88 grams, and that's total, right? Multiply that by 100 because this division will give us a decimal point representation of the percentage. Multiplied by 100 will give us the actual percentage. Again, we do that. 96.18 divided by 399.88. That gives us 0.24. We multiply that by 100 to give us 24.05%, or just 24%. That is the percent of sulfur in this molecule. So our answer is B, right? And again, you want to, for these type of problems, you want to do the exact same process. You want to first write down the molecule you have. You want to write down the atomic masses of each element. From there, you want to calculate the total amount of each element in the molecule, as we did here. Add them up to find the total weight, total molecular weight, and then based off of the element you want to find the percentage of, you take that element, divide by the total weight, and multiply by 100. Let's take a look at the next ones. The next calculation-based question is number 6. A chlorinator is set to feed 200 pounds of 12.5% sodium hypochlorite solution in 24 hours to a flow of 750,000 gallons per day. Find the chlorine dose in milligrams per liter, right? So with these dosage calculations, there's a couple steps that you want to follow. We know that we're going to be using the part per million equation. EPM is equal to pounds of chemical per million pounds of water, right? And this can be found right on our formulation sheet. Second page, we have our part per million equation, right there. Pounds of chemical per million pounds of water, right? So let's take a look at this step by step and first analyze what we are being asked to solve for. We know that we want the chemical dosage milligrams per liter, right? That's what we want, the chemical dosage. So we know we're looking for the part per million. The part per million is equal to 1 part per million is equal to 1 milligram per liter, right? So let's take a look at what we need, what we have, and how we get to our final answer. So what I like to start with, I like to convert the water, whatever water you have, I like to convert that to million pounds of water. That's the first step. The second step, you want to see how many pounds of chemical you have based off of the information you're given. So let's tackle this one step at a time, right? Let's first convert the amount of water to million pounds of water. So we have 750,000 gallons per day being processed, right? We want to convert that to million pounds of water. Well, we have to convert first to pounds, right? Let's take a look at our formulation sheet. We know to convert from gallons to pounds, we need to use a conversion factor. 1 gallon of water is equal to 8.34 pounds, right? That's the factor right there. So we want to arrange that in a way that the units cancel out. So gallons have to be at the bottom. 1 gallon is equal to 8.34 pounds of water, right? And a conversion factor that I like to use to convert to million pounds, 1 million pounds, right? That's equal to 1 million pounds. This last conversion is just to get those units in million pounds, since that is what the equation calls for, right? Now let's go through. We times by everything on the top, right? We multiply by everything on the top to get that on top, and then divide by the multiplication of everything on the bottom, right? Let's go through that first process there. 750,000 gallons, right? We multiply that by 8.34, right? And then multiply that by 1 to give us 6,255,000. Here we go, right? And all that divided by the multiplication on the bottom, and that's 1 million pounds, or just 1 million, sorry. We'll take a look at the units after, right? So we need to divide that by 1 million, right? To give our answer equal to 6.255 million pounds, right? Take a look at those units. Gallons cancel out with gallons, pounds cancel out with pounds, and we're left with million pounds of water. That's our units. That's what we have to plug into the part per million equation, right? So right now we have our million pounds of water. So we have the first part of the part per million equation, right? Let's write the part per million equation right up here. That's equal to pounds of chemical per million pounds of water. We have the first part. Now we want to find the pounds of chemical. In this case, the question is asking us find the chlorine dosage in milligrams per liter. So we want to find the pounds of pure chlorine in the solution, right? From the problem statement, it's asking us that it's 200 pounds of 12.5% sodium hypochlorite solution. Sodium hypochlorite solution is a liquid, so that's 240 pounds of liquid. It also gives us our percentage of chlorine by weight. That is 12.5%, and that is pure chlorine by weight, right? So let's take a look at how we would calculate the amount of pounds of pure chlorine in the solution. So we know we have 240, and that's pounds of solution. We know that it's 12.5% of that solution by weight is pure chlorine. So we want to multiply that by the decimal point percentage representation of that 0.125, right? And that'll give us our pounds of pure chlorine, right? So 240 multiplied by 0.125, that gives us 30. So pounds of chlorine equals 30 pounds, right? So now we have everything we need to plug into our part per million equation. And that's pounds of pure chlorine. So with that said, part per million, right? We have the pounds of chlorine, 30 pounds chlorine, divided by the million pounds of water, 6.255 million pounds of water, right? Do some quick math. 30 divided by 6.255, that's equal to 4.79 part per million, right? ppm. It's equal to 4.8 ppm when we round, right? So for this question, correct answer, 4.8. Answer is D. The next question reads, a water treatment plant treats an average daily flow of 400,000 gallons per day. GPD stands for gallons per day. The desired polymer dosage for coagulation is 2 milligrams per liter. How many pounds of polymer will be used in 60 days? So again, let's distinguish first what they're asking for. They're asking for the pounds of polymer used in a 60-day period, right? So we see a concentration. We also see a flow or water treated, in this case per day. So we know we're going to be using the part per million equation to find the pounds of polymer used, right? Let's again start with the part per million equation that can be found on the formulation sheet. So part per million is equal to pounds of chemical per million pounds of water, right? We're given the water treated per day, and we're also given the coagulation dose, 2 milligrams per liter. So in this case, we're given the ppm, and we're also given the million pounds of water. So let's first take a look at the water. We have 400,000, and that's gallons per day, right? Again, we use our formulation sheet to find that conversion factor. 1 gallon is equal to 8.34 pounds of water, right? Our conversion factor, we're using that one. There it is. And then we want our units in million pounds of water, right? Take 1 million pounds. That's equal to 1 million pounds. Basically just noting that 1 million pounds written this way is equal to 1 million pounds with the units of m pounds. So again, we want to multiply everything on the top and divide by the multiplication of everything on the bottom. So 400,000 multiplied by 8.34 pounds. That's 3,336,000, right? And on the bottom, we have 1 day multiplied by 1 gallon multiplied by 1 million pounds. So it's 1 million, right? We divide that, we get 3.336, right? Now let's take a look at those units. Gallons cancel out, pounds cancel out, and you're left with million pounds. Of course, that's million pounds per day. We're concerned with that million pounds, right? Could even write that as, yes, so million pounds, right? To get our million pounds of water that we need to plug into the part per million equation, right? So we have the million pounds now in the units we want. We have also the part per million dosage from the question, which was 2 ppm, right? 4 milligrams per liter, same thing. So we have both of these. Now what we want to do is we want to arrange the chemical equation, the part per million equation, to solve for pounds of chemical, right? So pounds of chemical, the equation rearranged, a little bit of algebra, part per million multiplied by million pounds of water. Now that we have our equation in the format that we want, we know we're solving for pounds of chemical, right? So that's equal to 2 part per million multiplied by 3.36 million pounds to get our pounds of chemical, right? Per 1 day. We already have 3.336. We multiply that by 2, which gives us 6.672, and that is pounds of polymer per every 1 day of operation, right? Since we're using that flow rate that is treated in 1 day, right? We're using that dosage that's required, 2 part per million. So with this, we need to take it one step further because the question asks how many pounds of polymer will be used in 60 days of operation, right? So we know that here, 6.672, okay, and that's pounds of polymer per 1 day, right? We want to find that for 60 days, right? Days cancel out, and we're left with pounds of polymer for that 60-day period, right? So 6.672 multiplied by 60, we get 400.32 pounds of polymer within those 60 days, right? That is our total amount. So if we look at the question, we know that our answer, D, 400 pounds, right? Now let's take a look at the next calculation-based question. This one is problem number 14. 14 asks, a filter has sand surface dimensions of 32 feet by 32 feet, right? How many gallons of water are filtered in 1 day at a rate of 4 gallons per minute per square foot, right? So let's talk a little bit about the units first and the dimensions. We know that we're finding a surface area since we're giving length times width, right? So what we are doing is we're finding that surface area in a square or a rectangle, right? Finding that surface area. We know that the plant has a rate of 4 gallons per minute flowing per every square foot of the sand filter, right? So the first step, we need to find that surface area dimension in units of square feet. So let's take a look at our formulation sheet. We know that we're given the length and the width, right? We're going to be using the equation for a rectangle. Since we're given 32 feet by 32 feet are the dimensions, the length times the width. So let's start with that. So the area is equal to the length multiplied by the width. In this case, the length is equal to 32 feet. The width is also equal to 32 feet. If we had been given a length in feet and a width in inches, we would have to convert the units of inches to feet, right? We want to have everything in the same units, right? So in this case, they are both in the same dimensions, feet. 32 feet multiplied by 32 feet, right? That gives us 1,024 feet, and that is squared. Because again, we are multiplying the units as well. We multiply the units. So feet multiplied by feet gives us square feet, right? That's our area, right? So the next part of the question that's given, it asks how many gallons of water are filtered in 1 day at a rate of 4 gallons per minute. Well, we can find the total amount of gallons per minute that's processed, right, within for that filter. So let's take a look. Let's take a look at that rate in gallons per minute, right? We're given 4 gallons per minute that is being filtered for every square foot, right? Every square foot of that sand filter is filtering 4 gallons for every minute. We have the total area of that sand filter, 1,024. So the multiplication to find the total flow for that whole area of that filter, we times it by 1,024 square feet, right? Our units cancel out, square feet cancel out with square feet. And we're given the total flow rate flowing through the whole filter, the 32 by 32, for every minute that passes. So let's take a look at that multiplication. 1,024 multiplied by 4, we're given 4,096, and that's gallons per minute flowing through the entire filter. Now let's take a look at differences between what we're given. We're given a flow rate per cubic foot, right? What we calculated, this is the complete flow rate for the entire filter, the whole 32 by 32 foot sand filter. When we're given a flow rate per cubic foot, and we're given the dimensions as we were here for the area, we can find the total amount of flow that's being filtered with respect to time, right? So that's what we calculated here. Now, the question, revert back to the question, how many gallons of water are filtered in 1 day? It's asking 1 day, right? Well, how many hours in a day? 24 hours, right? So we have to convert the 4,096 gallons per minute to gallons per day, right? So let's write that out. Gallons per minute, there are 60 minutes in 1 hour, right? And there are 24 hours in 1 day, right? We take a quick look at the units. Hours cancel with hours, minutes with minutes. We're left in gallons being processed per day, which is exactly what we want. The question asks how many gallons are filtered in 1 day at a certain rate, right? So again, we multiply by everything in the top and divide by the multiplication of everything in the bottom. Let's go through that. We have 4,096 multiplied by 60 multiplied by 24, right? 5,898,240, right? And that is in units of gallons per day. We take a look at our question here. That is, 5.898 million gallons per day. And again, they took that extra step of 5,898,240, right? Gallons per day, right? They took that extra step to convert it into units of million gallons per day. So that's 1 million gallons in 1 million gallons. Divide that by 1 million to get 5.898, and that's million gallons per day to give the answer of A, right? Now let's take a look at the next one. A water supply produces 4 million gallons per day of finished water and reports using 400 pounds of hydrofluorosilicic acid each day. Assume that hydrofluorosilicic acid is 23% pure and contains 79.1% fluoride ion. What is the concentration in milligrams per liter of fluoride ion? Okay, so this is a loaded question. Again, we're asked for a concentration, milligrams per liter, so we know that we're going to be using the part per million equation, right? We're given our flow or our water, 4 million gallons a day. We are also given our pounds of solution, right? That's 400 pounds of hydrofluorosilicic acid solution each day, right? We're also given the composition of hydrofluorosilicic acid, pure hydrofluorosilicic acid, 23%, and also we are given our percent fluoride ion in the hydrofluorosilicic acid molecule, right? That's 79.1% fluoride in that molecule. Okay, so let's take this piece by piece. Let's first start again by converting our water into million pounds of water, and also by finding how many pounds of pure fluoride chemical we are using, right? So let's go to the formulation sheet. We know we're using the part per million equation right here, right? Let's write that down. Part per million is equal to pounds of chemical, in this case, pounds of pure fluoride ion, right? Divided by our million pounds of water. And again, the question is asking what is the concentration in milligrams per liter of fluoride ion? So we're given a flow rate. Let's convert that to million pounds of water, right? That's 4 million gallons for every day, right? We know that from our formulation sheet. We need to convert that to pounds of water. We use the factor 1 gallon of water is equal to 8.34 pounds, right? We want to rearrange that. 1 gallon is equal to 8.34 pounds, right? We also want to further process that. 1 million pounds to get that in the units we want, and 1 million pounds, right? And you could have easily skipped this step by just leaving it in the units of 4 mgd, 4 million gallons per day. But I like adding them here like this to watch the units kind of cancel out to the units I want. So go through, we have 4 million gallons. We times everything in the top and then divide by the multiplication of everything in the bottom, right? Times by 8.34 will give us 33,360,000 pounds of water, right? So, and we divide that by 1 million pounds, right? To give us 33.36 million pounds of water. And again, it's always good to do a units check. Pounds cancel with pounds, gallons with gallons, right? We're left in million pounds for every day. That's a total amount of weight of water being processed every single day, right? So we have the first part of the equation of our million pounds of water. Now, to calculate the concentration of fluoride ion, we need to find the pounds of pure fluoride in the solution, right? For hydrofluorosilicic acid, again, let's take an illustration. Let's say this is the barrel of acid, right? 23%, that's this here, 23% is pure hydrofluorosilicic acid, right? That's 23% of the whole barrel is hydrofluorosilicic acid. The rest are additives, manufacturer trade secrets that make up the rest of that solution, right? We're concerned with that 23%, right? From that 23% of that hydrofluorosilicic acid, 79.1% of that is pure fluorine, pure fluoride, right? So the way we want to set that up to find the pounds of pure fluoride ion, we want to take 23%, right? That's the percentage of pure hydrofluorosilicic acid. Then we want to take multiplied by the percentage of the pure fluoride ion, 0.791, right? And we multiply that by 400 pounds of hydrofluorosilicic acid solution. So basically what we're doing here is we're looking for that pounds of pure fluoride ion. That's what that gives us here, pounds of pure fluoride ion, right? We multiply that, 0.23, multiply that by 0.791, right? And we multiply that by 400 to give us the pounds of pure fluoride ion, 72.772. That's pounds of pure fluoride ion. Now that we have the pounds, we can then divide that by the million pounds of water, plug it right into our part per million equation, 72.772 pounds pure fluoride ion, right? Divide that by 33.36 million pounds of water to give us 2.18 parts per million, right? Now 2.18, that can be rounded to 2.2, right? And we have our answer of B. Let's take a look at our next question. And it asks, a water treatment plant has a design flow of 5 million gallons per day. The sedimentation basin is 10 foot deep, 50 foot wide, and 150 foot long. What is the approximate volume of the tank, right? So again, what is it asking? It is asking us for a volume. It's asking us for the volume of that tank. So we're given dimensions. We're given the length, the width, and the height. So let's take a look at our formulation sheet and see which equation we need, right? And again, we're not going to be looking at area. Area is length times width, right? That's two-dimensional. We're going to be looking at volumes, right? We're given the length, the width, and the height, in this case, the depth. So we're going to be using the equation for a rectangular prism to find that volume, right? The volume equal to the length multiplied by the width multiplied by the height, right? Let's take another check at the units that we are given. Height is given in feet, width is given in feet, and length is given in feet. Okay, we are good. Everything is in the exact same units. So that's 150 feet multiplied by the width, which is 50 feet, multiplied by the height, or the depth in this case, 10 feet, right? 150 multiplied by 50 multiplied by 10, 75,000, and that's cubic feet, right? So what we have to do now, we have to convert to units of gallons since our answers are given in gallons, right? So let's take that the next step to convert that, right? Let's look at our conversion factors and how we can get to gallons. We have 1 cubic foot is equal to 7.48 gallons. So that's the conversion factor that we will be using, right? 1 cubic foot is equal to 7.48 gallons. 750,000, multiply that by 7.48. That's 561,000 gallons. And we have our answer C, right? So when you're doing these calculations, pay attention again to the units you're in, pay attention to what you're being asked to calculate, right? Let's take a look at this next question, calculation-based question. A 475,000 gallon tank is filled during a pumping test in 16 hours. What is the pumping rate? Okay, let's break this down. Now, the pumping rate, usually given in gallons per minute, gallons per hour, we're given both the gallons in the tank and a time, right? That's what we need to calculate the pumping rate. We need the amount in gallons or volume per time. So we have the very first part of it. We already have our answer in gallons. So there's no need to change the units on the 475,000 since that's already in gallons. But we do want to change. We know that during the pumping test, it was filled in a time of 16 hours, right? We want to convert that to minutes. So let's take our pumping, our gallons in the tank, 475,000, right? Gallons, and we know that we want our time in gallons per minute, right? So let's take 16 hours, right? Let's convert that really quick to minutes, right? We know that 1 hour has 60 minutes. Hours cancel out. 16 multiplied by 60, that gives us 960 minutes, right? So our pumping rate will be in gallons divided by those minutes. So that'd be 960 minutes, right? To get our pumping rate in gallons per minute. We quickly do that division. 475,000 divided into 960. Give us a flow rate of 494.79, right? Close enough. 400, or rounding up, 495 gallons per minute, right? And that's our answer. Answer C. Let's take a look at the next question. It says in a particular softening process, it takes 75 milligrams per liter of soda ash to remove non-carbonate hardness. If the soda ash is 80% pure, how much product is needed? Okay, so in this case, we're given the purity of the soda ash. We're given that 75 milligrams per liter of that pure soda ash it takes to remove the non-carbonate hardness, right? So let's write down what we have. We have the soda ash required, that's 75 milligrams per liter. We know that the soda ash itself, or the soda ash powder, the product, is 80% pure, right? That means that out of 100 pounds, right? If we're talking in pounds, 80 pounds are pure soda ash, right? This case, out of 100 milligrams per liter, we know that 80 milligrams per liter is the pure soda ash, right? So we know that the product is equal to the pure divided by the percent, right? Or another way of expressing this, the pure is equal to the percent multiplied by the product, right? We know that it's 80% pure, right? So 80% of that product is pure soda ash, right? It's just a simple percent multiplication to find the pure that we need. That was the same thing that we used for the problem where we calculated the percent sodium hypochlorite of pure chemical, right? Chemical pounds. That one was 12.5% of pure chlorine in that solution. For the hydrofluorosilicic acid, right? It was 23% pure hydrofluorosilicic acid multiplied by the percent of fluoride in the molecule, 79.1, right? It's the same concept. To find the pure, we take the percent that's given and multiplied by the product, right? So we're rearranging this formula to find how much product we need, right, to achieve the 75 milligrams per liter. So in that case, then we have the pure 75 milligrams per liter, that's pure soda ash, right? Divide that by the percentage in the decimal form, 0.8, right? To give us 75 divided by 0.8. That is 93.75 milligrams per liter of soda ash, right? That, rounded up, is equal to 94 milligrams per liter. And that's our answer. So this one's more of a basic concept of percentage of knowing the difference between what amount is the pure, the percentage of the product, and doing a basic multiplication or division of that percentage to find either the pure or the product, in this case the product, which was 94 milligrams per liter. Now let's take a look at the next one. So it asks a water storage tank 50 feet by 70 feet by 50 feet is full of water. If the water is being pumped out of the tank at a rate of 250 gallons per minute, how long will it take to empty the tank? Okay, so we're being asked for time. We're being asked for how long will it take? The storage tank is full. It's pumping at this rate. What is the time that it will take to empty it completely out, right? So let's take a look at the formulation sheet. Take a look and see what equation, what volume equation we're going to be using, right? So we're given length times width times height, right? So the volume equation we're going to be using, again, a rectangular prism, right? Length times width times the height, right? Let's write that down. Volume is equal to length times width multiplied by height, right? We're given those dimensions. That's 50 feet by 70 feet by 80 feet, right? So let's find this volume. 50 times 70 times 80. That's 280,000. And again, units, when you multiply the numbers, you're also multiplying the units. So feet multiplied by feet multiplied by feet, that gives us cubic feet. And that makes sense because we're looking for a volume. If we were looking for an area, that would be in units of square feet. So it makes sense that we're getting units of cubic feet since we're looking for a volume, right? Now that we have this volume, we have from the question that it's pumping at a rate of 250 gallons per minute. We have units of cubic feet. So we want to further change this to gallons so that we have everything in the same units, right? So let's take a look at what conversion factor we're going to want to use to convert this from cubic feet to gallons. We know that 1 cubic foot is equal to 7.48 gallons. That's what we're going to use. And again, we want to arrange the conversion factor in a way that units cancel out. So 1 cubic foot equal to 7.48 gallons, right? We multiply by everything in the top and divide by the multiplication of everything in the bottom, right? So with this, we get 2,094,400 gallons of water, right? We take a look at the units, cubic feet cancel, and that's in gallons, right? So from here, we know our flow rate, right? That is 250 gallons for every minute, written out from the problem statement, GPM, gallons per minute, right? In this case, we want to find the amount of time that it takes for the tank to be emptied, right? So we would want to start with 2,094,400 gallons, right? We are using the gallons per minute that's given in the problem statement, or the rate, as a conversion factor to find those minutes. We know that 250 gallons is being emptied for every 1 minute that passes, right? So we multiply by everything on the top and divide by the multiplication of everything in the bottom. In this case, we're dividing our 2,094,400 by 250, right? And we get 8,377.6 minutes. Again, we're paying attention to the units. Gallons canceled out. We have units of minutes, right? But the answers are given in hours. So we have to further change that 8,377.6 minutes and convert that to hours. So there are 60 minutes in 1 hour, right? So we divide by 60, 139.626, and that's hours, right? A problem that rounded up is 140 hours, which is the answer we get. Answer C, 140 hours. So again, we have to make sure that we're looking at those units to see what's being asked, what units they're in, before we make a decision on which is the correct answer, right? Now let's take a look at the last question, question number 35. It says how many pounds per day of liquid alum are used if the flow rate is 12.7 million gallons and the dosage is 8.25 milligrams per liter of alum. The dry alum percent equivalent is 48. So based off of this, we know that we're going to be using the part per million equation, right? Again, we start off with writing the part per million equation. ppm is equal to pounds of per million pounds of water. We're given the fact that it's producing, we're given the fact that it's producing 12.7 million gallons per day, right? So let's first convert that to million pounds of water. 12.7 or 12,700,000 gallons, right? I want to convert that to pounds. So if we look at our conversion factor, 1 gallon, 8.34 pounds. We arrange it accordingly, and we also convert to million pounds, which is what we need to input into the equation, right? So we have 12,700,000. Multiply that by 8.34, right? And then we divide that by 1 million. Give us 105.918 million pounds of water, right? And we have that first portion. We have the million pounds of water. And from the problem statement, it's asking us how many pounds per day of liquid alum are used if the flow rate is 12.7 million. So we're being asked for pounds per day of liquid alum, right? So this is where the percent of dry alum, the percent equivalent, is 48%. This is where this comes into play, right? Let's also write down the part per million that we already have, 8.25, and that's milligrams per liter. So we have this, we have the million pounds of water. Let's reduce our pounds of chemical equation, right? Part per million equation equals part per million multiplied by million pounds of water, right? So we can find our pounds of chemical. We have our part per million, 8.25 milligrams per liter, multiplied by the million pounds of water, 105.918 million pounds, right? 8.25 multiplied by 105.918 and gives us 873.82. So from here, we know that this, what we're calculating, this part per million, the part per million is pounds of alum. That's pounds of pure alum, right? Pounds of pounds of just alum, right? Since this part per million, 8.25, that is dry alum, right? And that this here is pounds of alum, So we want to find the pounds of the liquid alum, given the fact that the percent equivalent is 48% of the dry alum. So again, this reverts back to that purity situation, right? So we know that for the liquid alum, we're going to have alum pounds. We're going to have the dry alum pounds divided by the 0.48 or the percent, right? Now, why is this? Why is this? Because we're given in the problem statement that the dry alum percent equivalent is 48%. What does that mean? That means that 48% of the liquid alum is the dry alum, right? That's basically looking in terms of purity. 48% of the liquid alum is the dry alum in pounds, right? That's basically what it's saying. When it tells you that it's dry alum percent equivalent, 48%, or whatever percent is given in the problem statement, that's telling you that 48% of the pounds of liquid alum is the pure dry alum pounds. In this case, we found the pounds of alum. That's the pounds of dry alum, right? And we want to find the pounds of liquid alum that we're applying. So liquid alum is equal to dry alum, which we calculated 873.82 pounds of dry alum divided by 0.48 in a percentage form, 1,820.46, and that's pounds of liquid alum, right? For liquid alum, we have our pounds of pure alum, dry alum, divided by our percent equivalent of dry alum, right? To give us our total pounds of liquid alum, right on the bottom here. That gives us answer D of 1,820 pounds of liquid alum being processed per day, right? So I hope this was helpful in kind of looking at the math behind the question. And if you have any more questions, please feel free to reach out with any questions you may have on any of the calculations. Thank you.